So today we're going to take a look at section 3.4, okay, synthetic division and what's called rational zeros. Okay, so we're going to learn a method that helps you find all the roots of a polynomial as long as they are fractions. Okay? And we're also going to look at a quick way to do long division, but the method we're going to learn only works in certain cases. Okay? So it is a quick way to do it, but you can't use it all the time. All right, so first thing to try to understand here is when you're finding roots of a function, roots can be rational or they can be irrational. Here's a function that would have irrational roots. If I said, basically, tell me, if I had it written like this, okay, and I asked you to type this into a calculator, you're basically solving for where x squared equals 2. Okay, if you just add 2 and bring it to the other side. So if you try to solve that, what do you have to do to get rid of the exponent of 2? You have to take a square root. So the answers to this problem are the positive square root of 2 and the negative square root of 2. The two numbers that make this equation 0 are irrational. Okay, square root of 2 can't be written as a fraction. Okay, versus if you had something like this, just a simple linear equation, the answer here is rational. Okay? Negative 4 is the number that makes this 0. And negative 4 can be written as a fraction. All right, so some roots are irrational, some roots are rational. Well, there's a theorem that can help us find all of the rational roots. All right, so this first part here is just saying, suppose we have some polynomial. Okay? And I've written it in descending order, from the highest degree term all the way down to the constant. Right, so you might have something like 5x cubed plus 8x squared minus 3x plus 7. Okay, so you have some kind of polynomial. And there's a couple things I have to mention about it. So this part, it basically says, anybody remember what that upside down a means? All, yeah, for all. Okay, so for every value of n, okay, meaning the first one, the second one, the third one, the fourth one, all the different values of n you could have, okay, a sub n, that's the coefficients. A sub n minus 1, a sub n minus 2, all the way down to a sub 0. Every one of those numbers has to be rational. Okay, so in other words, all your coefficients have to be rational numbers. That's what this first statement is saying. Okay, it's just saying it using symbols. So all of your coefficients have to be rational numbers. And the other restriction is the first coefficient and the last coefficient can't equal 0. Okay, it's just a shorter way for me to write that. The first coefficient and the last coefficient cannot equal 0. Okay, so if we happen to find a rational root or a rational 0, okay, we can write that as a fraction. Okay, all rational numbers, that's what it means. You can write it as a fraction. And we could write it in the form p over q, okay, where p is some number, q is some other number. Okay, but there's a method to how you can find p and how you can find q based on the problem they give you. Okay, p has to be a factor of the constant. Right, so p is a factor of the constant, and q is a factor of the leading coefficient. So what's kind of interesting about the rational root theorem is the only two numbers in this entire polynomial that affect the rational roots are the leading coefficient, the first number, and the last number. You can change anything you want in the middle. and it would have no effect on the rational roots. Okay, now what this theorem does is it gives you a list of possibilities. I'm not saying that every single possibility here is going to be a root. Okay? This theorem gives you a list of options, and then you can use your graphic calculator to try to figure out, okay, which ones in that list of options work and which ones don't. Okay? But this is a method to generate every possible rational root. Okay? And then we'll use the calculator to narrow down which ones really work. Okay, so that's what I'm saying right here. Not every single number of the form P over Q is going to be a rational root. In fact, a lot of times you're going to generate 20 different possibilities, and maybe only one of them works. Okay, so let me show you with an example. Okay, we're going to list all the possible rational roots of this polynomial. Okay, so if there's a rational root, it can be written in the form P over Q. So I need to figure out all the factors of the constant, and then all the factors of the leading coefficient. Okay, so let's start with all the factors of the constant. Okay, what's my constant here? Josh? Negative 6. Okay. Whether it's a negative 6 or a positive 6, it doesn't really matter because the factors of those two numbers are the same. Can you tell me the factors of negative 6?
2, negative 3, 1, negative 6, something like that.
Yep. So go ahead, start with the lowest one again. And just stick with positives for now. 1, 2, 3, and 6. And he started to say some negatives, so of course you could have the negatives of all those as well. Okay, so when I say factors of the constant, those are all the factors of this constant. And now Q, those are the factors of the leading coefficient. Okay, Grayson, what are the factors of, well, what's the leading coefficient here? 10. And what are your factors of 10?
1.
Yep, 1, 2,
5,
10. And of course, negative 1, negative 2, negative 5, and negative 10 are also factors. Okay? Any number that divides into 10 without a remainder. Now, if there is a rational root in this problem, it's going to be of that form, P over Q. So what we need to do is write every possibility you could have. Any one of the P's over any number in the Q's. Okay, so there's a lot of different options. Okay, but if we use the positive negative symbol, that eliminates having to double the amount of things we would have to write. All right, so let's start with 1. Okay, let's say we pick that one. Okay, we could have 1 over what?
1.
Yeah, we could do 1 over 1. What else could we do? We could do 1 over 2. We could do 1 over 5. And we could do 1 over 10. So those are all the different possibilities for rational roots with 1 as a numerator. And I'm just going to reduce this and make it 1. Okay, now let's write all the different possibilities with 2 as the numerator. So we could have 2 over, yep, we could have 2 over 1. What else could we have?
2 over 2.
We could have 2 over 2, but we already have that one. Okay, so 2 over 2 is 1. What else could we have?
2 over 5.
We could have 2 over 5. And we could have 2 over 10, which is 1/5. So we already have that one. All right. Now let's do all the options with 3. Okay, so we could have 3 over 1. Yep. What else?
2.
Yep, we could have 3 over 2. 3 over 5. Yeah, I don't think we have any of these. And what else?
3 over 10.
3 over 10. And the last one is with 6. So we could have 6 over 1. We could have 6 over 2, but do we already have that one? 6 over 2? Yeah, so that gives me 3. How about 6 over 5? Do I have that one? Nope. And how about 6 over 10? I already have that one, 3/5. So, if this graph crosses the x-axis somewhere that's a rational number, it has to be one of those. Has to be. Okay? What's that?
How is this a shortcut?
Well, it gives you a starting point to figure out one root, and then once we figure out one root, then maybe we can use quadratic formula to find other roots or something else. But you have to be able to find at least one root to start. And this gives you at least a list of things you could try, and then we can graph it, and that'll help us narrow it down even more. All right? So any questions on what this list is? Okay, it's a list, again, if it crosses the x-axis at a rational number, it's going to cross at one of those spots. If, okay, maybe none of these are, maybe it has no rational roots. And in that case, it wouldn't cross the x-axis at any of these. Okay, but that's, when I asked you for a list of possibilities from the rational root theorem, that's exactly what I'm looking for. Okay, all the possibilities for P over Q. All right, so now I want to go back to this problem. And I'm going to show you how you can use this theorem to prove that a root is irrational. Okay, and we're going to use the graphing calculator to help us out. So that's the same problem we did in example 1. So let's graph it. I want you to prove that that problem only has one real root, and prove to me that it's irrational, that it's not rational. Okay, so I've got 10x to the 5th minus 3x squared plus x minus 6. So I'm going to graph it. All right, so what do you think I should do first there? About Jeff, any thoughts how I can use the graphing calculator to help me?
Find where it crosses the x-axis.
Okay, let's find where it crosses the x-axis. All right. So it crosses the x-axis at 0.9505. So now I know where it crosses. I want to prove that that's irrational. So how can I do that?
You said 0.9.
About 0.95. So based on what we did in example 1, anybody tell me how to prove that that number must be irrational? Yeah, exactly. That number that just came up on the screen, 0.9505, it's not any of these fractions. Okay? These are the only rational numbers that exist for this problem. Okay? So if you get a number like, we get 0.9505, if you get a number that's not in this list, it must be irrational. It has to be. Okay? Any questions on that reasoning?
So if it's a decimal, it's irrational.
No, because there are decimals in this list. Like that's 0.4, 0.5, 0.2, 0.6, 0.3.
So it's like if we're turning the fractions into decimals.
Yeah. So if you turned all these into decimals, you would not get 0.9505 for any of them. Okay. So since that number that was on the calculator is not in this list, and this is the list of rationals, that number must be irrational. All right. So that's what we write down. So the root is at about 0.9505, which is not in the list of rational roots. So 0.9505 must be irrational. Any other questions on that? Yeah?
What's Q? I don't Q coefficient.
Q. So if we want to go back, P is all the factors of the constant. Q is the factors of the leading coefficient. Hey, we're gonna do another one too. So. All right, so another thing we're going to take a look at in this section is synthetic division, which gives us a quick way to divide by something as long as it's pretty simple, okay? As long as it's of the form x minus c. So if you want to divide by like x squared or x cubed or something more complex, you can't use this method. Okay, but if you want to divide by something linear, you can. Okay, in the book, you're going to see this written. They use a different name for it. It's named after someone. Okay, they call it Horner's algorithm. Yeah, it's probably the guy who discovered it, I'm guessing, but most people call it synthetic division. Okay, so if you see a problem in the homework that says use Horner's algorithm to solve, that just means use synthetic division. All right, so I think the best way to do this is to kind of show you the steps and then do each step on a real problem, okay, as we're going through. Okay, so the first step is you're going to write down C, which is the number after the minus sign. Okay, so I'm going to write down the number that comes after the minus sign, and then I'm going to put a little bracket around it, and then I'm going to write down all the coefficients of f of x. Okay, and I'll fill in zeros for anything that I'm missing. All right, so example 3, it's worded a little bit differently. But basically what this problem is asking you to do is it's saying divide 2x cubed minus 5x squared plus x plus 3 by x minus 3 halves. Okay, remember all the different things that are equivalent. If 3 halves is a root, or if 3 halves is a 0, that's the same as showing x minus 3 halves is a factor. Okay. Does everyone remember that from yesterday? Okay. So I'm trying to show 3 halves as a root. So what I'm going to do is show x minus 3 halves as a factor. How do you show something as a factor? You divide it and hope that you get a remainder of what? 0. Okay, so I'm just going to divide this in and hope that I get a remainder of 0. So take the number after the minus sign, which is your root. Okay, put that on the outside. And now write down all the coefficients of your numerator. Okay, am I missing any terms? You think, Francisco? Nope, I got them all. So I'm going to put a 2, negative 5. What's the coefficient on x?
1.
Yeah, it's just a 1. Can't forget that. And a 3. Right, so that's step 1. Step 2, bring down the first coefficient. So I'll give people a second to copy that. Okay, bring down the first coefficient. Okay, and I like to put a line because it's going to separate some of the arithmetic I'm about to do. You don't have to, but I think the line kind of helps. Okay, what's nice about synthetic division is everything I do now is going to basically fit inside this box. Okay, it's not like a long division problem where it just keeps going down the page and like further to the right. this pretty much is the space I'm going to need to do this problem. So that's one nice thing about synthetic division. It doesn't take up as much space. Okay, it says multiply the divisor, okay, the number that's in that little bracket, by the first coefficient you just brought down, and you're going to write the result below the second coefficient. Okay, so let's do that. What's 3/2 times 2? What is it? 6/2, which reduces to 3. Let's try writing with real numbers. 3. Okay, so I multiplied the divisor by the first coefficient, and I put the answer right below the second coefficient. Okay, and now kind of part of the same step, still in step 3, is to add the number that we just wrote, 3, and the one that's right above it. So now we're going to add up the two numbers in this column. What's -5 plus 3? -2. Okay. And now we're going to repeat, okay, until we're done. When we're done, I'll explain to you what this bottom row means. Okay, so we'll come back to that in a second. All right, so next step. Now do 3/2 times -2. Okay, Tom, what's 3/2 times -2? -3. And now add this column. Pacey, what's +1 plus -3?
-2.
Yep, -2. Okay, now we're going to do it again. Josh, what's 3/2 times -2?
That would be
-3. And what's 3 minus 3?
0.
0. Now, what was I hoping to get on this problem for a remainder? Remainder of 0? What do you think this last number is? That is my remainder. Okay, so the last number is your remainder. The other numbers here are the coefficients of your quotient. Right? Starting with, on the right side, this is your constant, this is your linear term, this is your squared term. Okay, so the quotient here would be 2x squared minus 2x minus 2. Okay, so these numbers that I'm circling right here are these numbers right here. Okay, you just have to count and figure out what's your highest power. Okay, that's your constant all the way on the right next to the remainder. Then the x term, then the x squared term. All right, so we got our quotient, and the last number, as I said before, that's your remainder, and it is 0. Hey, so any questions on that one? All right, let's try. We'll try another one. This time, I want you to use synthetic division. That's what SD is, synthetic division, to find the quotient and the remainder. When I divide this by that. Okay, so what number is going to go in that little bracket? Right, because you always have to put the number that's after the minus sign in the denominator. Think of x plus 3 as x minus 3. Okay, and what about the coefficients that I'm going to write next to -3? Yep. 3.
You have to put a 0.
Yes.
So 0, 1, -11.
-11. Yep. So always make sure that if you you fill in any zeros if you're missing powers. All right. So we've done that. So we're good. Okay. What's my first step? Yep. Bring down the 3. That just kind of gets everything going. And now we're going to multiply, write the result, and add, and keep repeating that. All right. So Jeff, what's -3 times 3? and then add 7 to it.
-2.
-2. Okay, now Francisco, if we multiply -3 times -2, 6, and then add 6. Pacey, -3 times 6.
-18.
Okay, and add
Oh, -17.
here's 17. And the last one, -17 times -3, 51, and add 40. So let's see if we can interpret that and tell me the quotient and the remainder. Okay, what's my quotient here? Well, yeah, go ahead.
3x squared, 3x cubed.
Yep, 3x cubed.
2x squared plus 6x minus 17.
Perfect. That's my quotient. And what's my remainder? 40. Yep. So a lot faster than doing long division. But again, it only works if you're dividing by something that's x minus a number or x plus a number. And be careful with x plus, because you have to rewrite that. Okay. So now, if I asked you kind of a follow-up to that, is x plus 3 a factor of 3x to the 4th plus 7x cubed plus x minus 11? No. How do you know it's not a factor? Yeah, it didn't go in without remainder. If it did go in without a remainder, and I asked you to factor this problem, you now know one of the factors. Okay. All right, I want to show that 3 is not a 0. Okay, so in other words, I want to do, actually you tell me, I'm taking this, and what am I really dividing by?
You divide by x minus 3.
X minus 3. So in other words, show me that x minus 3 does not divide into this. And to show that it doesn't divide into it, what do you have to look at? Tom? Or, yeah, go ahead.
The remainder.
Yeah, look at the remainder. All right, so I'm hoping that I get a remainder that's not what?
Minus 0. Or you want to,
Do I want 0 or I don't want 0?
or you don't, well, for this question, you don't.
I don't. I want to show that 3 is not a root. Show that the graph does not cross the x-axis at 3. Show that this is not evenly divisible by x minus 3. All those questions I just said are exactly the same process to solve. Okay, let's do our synthetic division. Put the root on the outside. That's the number after the minus sign. Write down your coefficients. I'm not missing anything. And again, once you get good at this, it's really pretty quick. So bring down your 2. 3 times 2 is 6. 5 and 6 is 11. 3 times 11 is 33. 33 minus 2 is 31. Times 3 is 93. Minus 3 is 90. That's the whole problem. Okay. The only thing that can really slow you down is when the arithmetic gets bad, or sometimes I make a mistake because I do it a little fast. But any questions there? So what tells me here that x minus 3 doesn't divide into the numerator? What tells me that 3 is not a root? There's a remainder of how much? 90. That's my remainder, and it's not 0, which proves what they asked me to prove. 3 is not a root. Now, this isn't a good way. You don't want to try this method guessing. Is 4 a root? Is 5 a root? Is 6 a root? That's not a good approach to try to find a root. Okay, for that, we'll use the rational root theorem combined with a calculator and this. Okay, so your strategies for finding rational roots. Okay, first you start out with the rational root theorem, which gives you a list of possibilities. Then we can use the graphing calculator to narrow down which of those possibilities work and which ones don't. And then if we find one that works, we can use synthetic division. Okay, because remember, if you can find one thing that's a factor and you divide through by it, it helps you to find more factors. Okay? Just like I did earlier with the number 12. If I tell you 3 is a factor, and you divide through by it, you'll find another factor. Right? So we're gonna take that kind of same approach. So I want you to find all the roots for this cubic. X cubed minus 3x minus 2. Okay, so if we can't find a rational root here, we're probably going to be stuck. Okay, you have to be able to find at least one rational root, which is going to allow you to use synthetic division. And when you divide through by a root, it takes the exponent down one notch. So if you come down from a cubic, what do you turn into? A quadratic. And if I can turn this into a quadratic, then I have all kinds of methods to solve it. Maybe I can factor it, I can at least use quadratic formula, but I got to turn this cubic into a quadratic first by finding one rational root. So I'm hoping we can find one. So let's start with our list of possibilities, and then we'll try to narrow it down. Okay, P is the factors of the what? Yep. P is the factors of the constant. This time, what's my constant? Negative 2. That's a much easier number to work with than the first one. What are the factors of negative 2? 2 and 1. Yeah, that's it. Okay, and Q is the factors of what?
The leading coefficient.
The leading coefficient, which in this case is a 1. So what are your factors of Q? 1 and negative 1. So we're not going to have a lot of options here for roots. Okay, so I'm just going to make a list of possible rational roots. Okay, I could have 1 over what? Yeah, you could have 1 over 1. All right, that's it. And what else could you have? 2 over 1. So there's only 4 possibilities for rational roots here. Positive, negative 1, positive or negative 2. If there's a rational root, I guarantee you it's crossing the x-axis at one of those 4 numbers. Okay, so that helps me because now when I graph my function, I know I'm not looking for a rational root out at like 200. So I can just use a standard window, and I can see everything I need to see. Okay, so that kind of helps me. So type in our problem. So we've got x cubed minus 3x minus 2. I'll just do zoom 6. And where does it look like it crosses the x-axis? That could be one of our rational roots. I think positive 2 looks like a root. Yep, and what else? And what about negative 1? We talked about this kind of behavior when it comes up and it kind of bounces away from it. Well, it just barely touches that maybe at negative 1 and goes away. I'm not sure, but it looks like it just touches it and goes away. So what does that mean?
That means that root is repeated.
Yeah, I'm thinking that possibly at negative 1 we have a repeated root. So before I even start the problem, I'm already thinking the roots are negative 1, and 2. Those are the 3 answers. But let's pick one of them. Let's try 2. And let's divide through synthetically by it. And if we get a remainder of what, it'll confirm that it is a root. 0. So let's try dividing through by 2. Let's write our coefficients. Okay, what would my coefficients be? 1, 0, negative 3. Because if you forgot the 0, you probably wouldn't get a remainder of 0, and then you'd think 2 doesn't work just because we forgot the 0. All right, so 1, 0, negative 3, negative 2. Okay, bring down my 1. 2 times 1? 2 plus 0? 2 times 2? Minus 3? Times 2? Minus 2. Okay, so it works. Now, I'm interested in the remainder because I got 0, but I'm also interested in this. Okay, because now I know x cubed minus 3x minus 2 factors as, what do we get, what do we know absolutely is one of the factors? Based on what we just did. 2 is a root, so that means what is a factor? X minus 2 is definitely a factor. And where does the other factor come from? We already did the work to find it. Yeah, the quotient. Okay, remember, if you know a factor and you divide through by it, the answer that you get is another factor. Okay, like 15, I tell you 5 is a factor. If you divide 15 by 5 and look at the answer, that's another factor, 3. Okay? Here's what I got when I divided through by my factor. I got x squared plus 2x plus 1. And now we can factor that even further, and I think we're going to end up getting what we expected. How does x squared plus 2x plus 1 factor? X plus 1. X plus 1. So when we look at our roots, we already know 2 is a root. We confirm that. And we don't have to do synthetic division again because we were able to factor it. So now we can just set each factor equal to 0 and solve. So what's my other root? -1. And what's special about this root? It repeats, which is exactly what we thought by looking at the graph. Okay, -1 is a repeated root. Now you could have done the synthetic division differently. You could have said, well, I'm going to try dividing through by -1 to start. And you would have been able to go through the exact same process. It's just your quotient would have been a little different. Okay? It would have factored a little different at the end. But you would have still gotten the same answer. Okay, so any question on how we generated a list of possibilities? You can use the calculator to kind of narrow down which one we want to divide by. And then from there, we were able to factor. All right. So let's see if we do that. I'm not as concerned about what's called upper and lower bounds. I'm more concerned about finding roots. So let's just stick with that. All right. So let's find all the roots here. Okay. What should my first step be?
Irrational roots.
Yeah. Let's do the rational root theorem and find everything we can from that. And remember, they're just looking for rational. In some problems, they're going to ask for all of them, all the real roots. Okay, but in this case, they only want the ones you can write as fractions. So from the rational root theorem, what are my factors of P? That's it. What are my factors of Q?
Plus or minus 1, 2, 3, 6.
Yep, plus or minus 1, 2, 3, 6. Okay, so all my fractions of the form P over Q, let's write those out. We could have 1 over 1, positive or negative. What else? 1, yep, positive or negative 1 over 2. 1/3, and okay, so if this graph is going to have a rational root, it's going to cross the x-axis at one of those 8 spots. Again, because all those numbers are really between 1 and -1, I can look at a standard window, and everything I need is going to be within that window. At least for rational roots. All right, so we got 6x cubed minus 5x squared plus 3x. Thank you, minus 1. Okay, and this is a little hard to look at, 1/2 and 1/3. Those are kind of close. So what I'm going to do is I'm going to zoom in a little bit. I can't really tell if it's, I think it's a half, but if I zoom in, it might help me a little bit. Yeah, I would say it looks like it's a half. So now that I think it's a half, what do I want to do with the number 1/2?
Well, it's phonetically divided from, well, it's a root,
You were on the right track.
you want to turn into fraction, divide that factor from the original problem.
Yeah. So I'm thinking 1/2 is a root. So that makes me believe x minus a half should be a factor. Now I'm going to divide through by x minus a half, and it's going to turn that cubic into a quadratic, which I can work with if I need to, but I don't think I'm going to need to because it looks like this only crosses the x-axis in one spot. Okay? So if it only crosses in one spot, that quadratic would probably have imaginary answers. All right? So put your 1/2 on the outside, and your coefficients. Not missing any. 6, -5, 3, 1. That's you. Okay, so do our synthetic division. What's half of 6? 3 plus -5?
Isn't it -1?
Oh, was the last number negative? Thank you. Didn't mess us up yet, but it would have. What's half of -2? Plus 3. And half of 2? And plus -1? 0. So we just proved that x minus a half is a factor, which means 1/2 is a root. All right, so I know x minus a half is a factor, and the other factor is 6x squared minus 2x plus 2. Now, you could try to solve this using quadratic formula, but watch what happens. All I'm going to look at is one part of the quadratic formula. Okay, watch what happens if you do that. What's b squared? 4 minus 4 times what's a? 6. And what's c? So I'm going to end up with 4 minus 48. That's a negative number. Okay, I'm going to have the square root of a negative, which means the other two answers are imaginary. So there are always 3 answers. There's always 3. But the problem is the other 2 would be imaginary. There's only 1 that's real. Well, actually, specifically this time, there's only 1 that's rational. Okay, so any questions why I'm not continuing on with quadratic formula there? They're imaginary. Okay, tomorrow we would continue on and get the other 2 answers. Okay, but not for today. All right, so I think let's do this one and then see where we end up. All right, so this time they don't just want the rational; they want all real roots. Okay, all real zeros. Okay, so what's always my first step? Yep, always do your rational root theorem. Kind of gives you an idea of where your roots could be. Okay, factors of p in this case. Positive, negative, 1 and 2. And factors of q. 1 and 3. Now I need every combination of p over q. Okay, what's one thing I could have? Yep. Yep, 1/3. What else? 2. And 2/3. So if this graph crosses at a rational number, it's somewhere between 2 and -2. That's my limit on my x-axis. Okay, let's type it in and see what we get. All right, so we have 3x cubed minus 8x squared plus x plus 2. Okay, so based on, well, let's just zoom in a little bit. right, so looking at that graph and our possible rational roots, does anybody have what they think a reasonable guess would be for a rational root? Positive 2/3. What I like to do too is I'm just going to check it. I'll just hit trace, type in 2/3. 2/3 is a root. But I still need to divide through by it because I need the quotient in order to get the other roots, okay, which are here and here. It almost looks like negative 1/3 could be a root, so you could check that one, but it's not. Okay, so this, to me, it looks kind of close to negative 1/3, but it's not. And what's that? Negative 1/2. It could be. I don't think that one works either. So I'm not seeing this number in this list. So that means this is probably what kind of root? It's probably irrational. And so is this one. All right? So we know that we do have one that's rational at 2/3. So let's do that first. 2/3. Am I missing any numbers? Nope. 3, -8, 1, 2. Okay, so bring down my 3. What's 2/3 times 3? What is it? 2. Yep, it's going to be 2. Okay, and then -8 plus 2, Jeff? -6. Okay, and Tom, what's -6 times 2/3?
-2.
Right, think of it as -12/3, okay, which is -4. And then -4 plus 1, Pacey?
-3.
-3. And what's 2/3 times -3?
-2.
-2. Add those up, we get 0. Okay, so now in my list of roots off to the side, I'm going to put 2/3. And it's said to label it as rational or irrational. What's that one? That's rational. Yeah. Now, the only way to get the exact answers is with synthetic division. Yes, I could use the calculator and get decimals. But if I ask you for an exact answer, the calculator can't do that. Okay. So now I'm going to do quadratic equation on that factor. Okay, so x minus 2/3 is a factor. And the other factor is your quotient. 3x squared minus 6x minus 3. Now I know this isn't imaginary. One, I could check b squared minus 4ac quick in my head. And I already saw the graph. It crossed the x-axis. So this square root has to come out positive, and it's going to be irrational. Okay. So let's set up our quadratic formula. We've got negative b plus or minus, what comes next? B squared minus 4ac, all divided by 2a, which is 6. Okay, and hopefully you notice pretty quick, you're subtracting a negative, so it turns to a positive. Okay, what's 4 times 3? 12. 12 times 3?
36.
And what's 36 plus 36? 72. Okay, can you simplify the square root of 72? Is there a perfect square that goes into 72? So yeah, you can check, try dividing it by numbers that are perfect squares. And if you do, check 9, it does work. Okay. So you can write the square root of 72 is the square root of 9 times the square root of 8 all over 6. But what's the square root of 9?
3.
So 6 plus or minus 3 square roots of 8 over 6. But what can I reduce everything by? 3. Becomes 2, 2, and that's gone. Okay, so you should get 2 plus or minus root 8 over 2. Those are the other two roots, and these are irrational. let's just check one of them. Let's take the square root of 8 plus 2 and divide by 2. So there should be a root at about 2.414. Let's calculate the root and see if that's where it is. So second calc 0. It's going to take me a second to get over there. Nope, it's not going to be 2. Oh yeah, it's probably going to be 2.414. 2.414. All right. And you could check the other irrational root, but it will be that one over there. So you can kind of check your answer with the graphing calculator. You just can't get that using the graphing calculator. Okay, the only way to get that, you're going to use your synthetic division and quadratic formula. Okay, so any questions on that one? All right, so I think that's probably a good stopping point. So tomorrow, pretty much the same thing, except we're going to extend everything we've learned this week to imaginaries. You can do synthetic division with imaginaries. You can factor with imaginaries. It's basically all the same stuff, just finding all the answers, not just the real answers. All right, so there's this upper and lower bound theorem, but we're going to skip over that. Okay, so on the homework, let me just adjust. Okay, so you don't have to do 31 and 32. Okay, so homework tonight on page 183. 1, 2, 5, 6, 9, 10, 13, 14, 17, 18, and 27. Okay, so we'll do section 3.5 tomorrow. I'll be after school if you need help, and we'll have our test on Friday.